Welcome to my video. In this video I'm going to show you the interface of the explainable predictive maintenance prototype I've made as part of my master thesis. It consists of 3 different interfaces that all have their own purposes, and what you see here is the most basic one, the monitor interface. In this interface you can select different engines. We have a total of 5 engines you can choose from. And once you've chosen one, it will basically run in the background. It will simulate that an engine is running, different data is coming from different sensors, and the model starts to predict for every cycle when it will fail. We see here the engine has failed at cycle 155. The blue line is the predicted remaining cycles, and the blue area is the lower and upper confidence bounds. Additionally to this, you can change a warning level. So in real life, you would want to stop maintenance before you would want to stop an engine before it actually fails. So you can perform maintenance and prevent failures. In every case, it will be different. So you have a slider here to determine when the warning level should be displayed. So here you see it, the engine should be maintained, and afterwards it will say it has failed. Additionally to this, you can show the contributions of the parts to the prediction. So the idea is when the model receives data, and it will give some output, but you actually want to know which parts in the engine have contributed now the most to this prediction. And you could use that to monitor which parts are degrading faster than others and maybe causing the failures. So what you see here is a schematic of the engine with green and red dots. A green dot means that this specific part is contributing positively to the prediction, so it makes the remaining cycles higher. Well, the red dot means that it's actually lowering it, which worsen the amount of remaining cycles according to the model. And what you see over time, the green dots disappear, become smaller, while the red dots are becoming more numerous and increase in size, which means over time more parts are contributing negatively to the prediction. So after a while, your engine has failed and you would like to do some analysis on it. You actually want to diagnose what was wrong in the engine. So you can go to diagnose mode from the monitor mode. And what you see here is the same prediction curve we saw before. And what the application does, it looks at this curve and compares it to other curves he has seen before and suggests which failure in the past is most similar to this one. And we can see that the application found that the failure seems to be most similar to historic failure in engine 93. Now, we can overlay the curve of engine 93 on this plot, and we see they are quite similar. And the idea behind this is you have a new failure, you want to explain how could this failure happened, and maybe you even want to fix it right away. And if you then find failures in the past that were quite similar to this one, you maybe can use the explanations of that historic failure and apply it to this engine, and it might work. So maybe in the past you had to replace the nozzle of engine 93 after it has failed. Now, that might also be true for this one. So this can give you an initial start for your root cause analysis and how to fix it. Additionally, you can overlay the true remaining cycles. It's this red line. What this means is if the model has predicted 100% accurately, it would have predicted this line. However, conditions could have gone worse over time, which could not have been foreseen before. So what you see here, this is quite steady, and then here it drops. Maybe something happens here, which we do not know, but this gives a sense of how accurate our model was. And what you see is most of the red line was in the 95% prediction interval. If we go back and select a different engine, what we will see is a different view. So in the previous engine it was overestimating, and in this one it's generally underestimating, but in the end they often converge. And also for this you can show the historic predictions of another engine. This was in this case 92, and you see that those are also quite similar. Something else you can do in this interface is look back at different cycles and ask what the prediction is, and also the contributions of the parts. So for instance, we select cycle 190. The prediction was 98.9 with 114, and it will now generate the engine plot, and we can see how the different parts have contributed positively and negatively on the prediction. And if we go further in time, we will see more red dots which are bigger. So at the end of the lifetime of the engine, we get these contributions of the different parts. We can go one level deeper. So now we only look at the parts, but we can actually look at the different sensory data. And then we get this plot, and these are all the different features the model uses to predict the remaining cycles. And what you see here is the model takes a base value. It's around 108. It's the mean prediction. If the model had to play really safe, it would always predict around 108. And we can see here how the different features push the prediction towards the left. So it influences them negatively. And in the end, we end up with a prediction around here, which is 6.1. And in the top, you see the most contributing features, and below you see the least contributing features. So what we can make of this is that cycle, which is time, was the most contributing feature to the failure. Then we can see static pressure at HPC outlet, ratio of flow to PS30. And we can actually check this with the engine plot. So static pressure at HPC outlet had a big negative influence on the prediction. And we can check the parts HPC, and you see a big red dot, which means it was negatively contributing to our prediction. So what an engineer could do with this is ask the model, okay, why did you think the model has failed, the engine has failed? And what it shows is that HPC is a large negative contributor, which can mean that HPC is the cause of this failure. So this could be a good initial starting point for performing maintenance. Additionally, what we can do is also show the different engine plots and the decision plots of the historic failure. So engine 92 at the specific cycle. So you can compare the contributions of two predictions of different engines and how they might be similar or different. And in this case, we see that they're quite similar. So maybe the reason why this engine has failed can also can explain why this engine has failed. So when you're done with diagnose mode, you click this, ready with diagnose, and then we can go on to the what if mode. And the what if mode is basically a small playground where we have the model and we can feed it different input values, and we can see what the effect is on the prediction. So we can start changing these values, and on the left you see that the prediction is changing as well. So what you can do with this is explore how the model behaves on different input values, even input values that wouldn't occur in real life. And these ranges also go beyond what the model has seen in the training set. So you can get a feel of how the model predicts outside of the ranges it has been trained on. So what we see here is the engine plot. And we can also show you the decision plot as well. Let's see. And additionally, we have the measure plot, which is something I quite like. What this does is you can select a measure, one of the features that the model uses to predict remaining cycles, and it will plot it on the x-axis at different values, and it will predict the remaining cycles at different values, while all these other values stay the same. So if I now would select cycle, we probably see a different plot. Yeah, we see a small difference whenever we change these values, which indicate that the relation between physical core speed remaining predicted cycles is dependent on other values. You can do this for other values as well. So what if we decrease cycle by substantially, we see that the relation comes quite flat. And this is a great way to explore the non-linear relations that the model has learned to predict its target value. Yeah, so you see that this has a lot of influence. And this is great to play around with and learn how the model and learn what relations the model has learned. So yeah, this has a lot of influence. So what you see, I'm just changing values. You can imagine someone who has a lot of domain knowledge on maintenance of engines can actually use this to test their own knowledge and see how it is reflected or rejected by the model, so that the engineer can actually update his own mental model of the predictive model, and maybe can spot some irregularities or even learn from the model relations that he did not find himself. This was a showcase of the explainable predictive maintenance prototype. Again, this is part of my master thesis, so if you would like to learn more about the different techniques I used and how this can be valuable, I refer to my master thesis. If you have any questions on how to run this on your own machine or other questions regarding my thesis, please let me know.